Here in chapter 20, we are going to start talking about magnetism. Um, First of all, let me tell you a little bit about the history of magnets. Magnetism was first discovered a couple hundred years BC, 200 or 300 years BC. They found a rock that had an attractive property to similar rocks and to other metals as well. And this rock was discovered in a country called Magnesia. And so these were called magnets because of where they were found. Okay, so there's a little bit of history there. What do we know about magnets? Well, magnets have two ends or poles. We call these north and south because, for some reason, which I'll explain in a couple minutes, one end of the magnet is attracted to the north pole of the Earth, and the other end is attracted to the south pole of the Earth. Now, this is actually rather similar to the electricity we talked about earlier. Remember how electricity, we said that if you have two positive charges, they repel, two negative charges repel, but if you have a positive and negative charge, they attract. So in other words, like charges repel, but unlike charges attract. It's the same with magnetism. Two like poles are repulsive, whereas two opposites are attractive. Sorry, I was trying to get my pen to work. It's not working right now. We'll do this. All right. So like poles are repulsive, but opposite poles are attractive. So a north pole is attracted to a south pole and vice versa. Now, it is similar to electricity, but there is a very huge difference. That difference lies in the fact that if you separate a positive charge from a negative charge, what do you get? You get a positive charge and you get a negative charge, completely separate of each other. They exist independent of each other. But with a magnet, if you take a magnet and you cut it in half, what do you get? You get two magnets, each with a north and a south pole. If you divide those in half, you get two more magnets, each with a north and south pole. You cannot separate a north pole from a south pole of a magnet. That is physically impossible. So what does the field attraction, the magnetic field of attraction look like? Well, by convention, we always draw lines going out of a north pole, but into a south pole. And these lines connect and they create loops, like so. Actually, not too different from what a positive and negative charge would look like with an electric field. But anyway, this is what you would see magnetic field looking like, always going from north to south. Now here's an actual demonstration where someone took iron filings, little dirt particles that are just iron that's found inside of dirt, and they just spread it out on a piece of paper and put a magnet on top. And you can see that the iron filings very clearly follow these magnetic field lines. And then here we've got a magnet, and you can see the needle is following in the direction as well of the magnetic field. Okay. Now, the Earth itself has a magnetic field, and it's rather important that we do have one. It protects us from a lot of high-energy solar particles. I'll explain that one in just a second. But yes, the Earth has a magnet. The Earth has an iron core that, as it rotates, it generates a magnetic field around the Earth. Now, you have noticed that this magnet down here seems backwards. South is on top and north is on bottom. That's not a mistake. Let me explain. Remember that we said that when you have a magnet, the North Pole is attracted to the North Pole of the Earth. Well, that's kind of ironic because opposites attract and likes repel. So if the top of the Earth were the North Pole of a magnet, then it would actually be repelling the North Pole of your magnet that you have. And so when we say that the north pole of a magnet is attracted to the north pole, attracted means that they have to be opposite. Therefore, really, the north pole of the Earth would be the south pole of the Earth's magnetic field. Likewise, the north pole of the Earth's magnetic field is near the south pole. And that has to be the case so that our convention of north pole of a magnet pointing north will still hold. Now, if you were to look closely in between two magnets, the north pole and the south pole of magnets, then what you would see, let me get back to my red color, is that the magnetic field lines pretty much go straight from the north to the south pole. It's very similar to what we saw with the electric field within a capacitor. On the ends, they do bow out slightly, but on the inside right here, they are pretty much just straight lines. All right, so now let's talk about what about what makes a magnet a magnet. We'll talk about something called a ferromagnet, which is a material that can become strongly magnetized, such as iron or nickel. We're going to look at this, at these materials, this iron and nickel, as if they're made up of tiny regions called domains, and you have an orientation, a tiny magnetic field, if you will, within each domain, and it looks something like this. And you can see that normally within each domain, the magnetic field is completely random. They're just pointing in all sorts of different directions. This would be just any normal material. Doesn't really do anything. However, if this iron were softened, slightly melted, and placed in a very high magnetic field while it hardened, well, these domains could change around, and then pretty soon all of these domains would change so that they're oriented in the same direction. And once they're all oriented in the same direction, well, then their influence on surrounding matter becomes stronger, and you've got yourself a magnet, a ferromagnet. Ferro coming from the root for iron magnet, so it's an iron magnet here. That's really what causes magnetism, is that these little domains, these regions inside of a material are all aligned in the same direction. All right, experiments have shown us that electric currents can actually produce magnetic fields as well. So here you've got in this image, let me get to my laser pointer, you've got in this image a wire which is exposed here. There's a current running through the wire, and as a result, you've got a magnetic field around, and you can see that easily with the compasses around the wire. Okay. Here's another figure showing iron filings on a piece of paper with a wire sticking through, and it generates a very strong magnetic field around the wire. In a diagram, this is what it looks like. From here on out, we are going to need to look at three-dimensional vectors. So in the next video, I'm going to show you a little bit more about three-dimensional vectors. But in the meantime, think of it this way. You have a current that's flowing upwards. You're going to have a magnetic field that flows this direction. Well, that's easy to kind of show in a picture like this, but how do we tell by ourselves? We use something called the right-hand rule. There are two versions of the right-hand rule. Let me first tell you this one here. The first right-hand rule is that you take your right-hand thumb, point it in the same direction as your current, then your fingers will be wrapping in the direction of the magnetic field. So if I were looking down on this, so the thumb would be pointing up towards me, I would see the magnetic field wrapping around the wire in a counterclockwise direction. Same direction that your fingers are going. It's important that you use your right hand for this. A left hand will give you the opposite direction, which is not what you want. So use your right hand, stick your thumb in the direction of the current. The fingers will wrap in the direction of the magnetic field. We can also look at the magnetic field around a loop. So here we've got a loop of wire, and we're going to assume we have a current that is flowing in this direction. And as we point our right-hand thumb in the direction of that current, then you'll see that your fingers are pointing left to right in this example. And no matter where your hand is, with your thumb in the direction of that current, your right-hand fingers are going to curl left to right. So that gives us a picture that looks something like this all the way around. This would be the magnetic field through a loop of wire, the same loop that we have in the left-hand figure. Now, mathematically, we're going to indicate these magnetic fields using a capital letter B. So why we use a B, I'm not too sure. That's okay. It will work. So whenever we use B mathematically, that's going to indicate our magnetic field.